Dr. L. Jones Torsius Thos, Professor of Mathematics, College of Engineering Gindi, Anna University, Chennai. He has obtained BSc and MSc Mathematics from Madurai Kamaraj University and PhD from Indian Institute of Technology, Bombay. He has served as NBHM Postdoctoral Fellow at Indian Institute of Technology, Bombay, and then as visiting faculty at University of Tennessee, Knoxville, USA, and Colorado School of Mines, Golden, USA. He is currently working as a professor in the Department of Mathematics at Anna University, Chennai. His research area includes numerical analysis of ordinary differential equations and partial differential equations. He has published more than 25 research papers in reputed international journals. He has visited many countries like USA, UK, Italy, Malaysia to participate in international conferences. He has completed DST SCRB funding project.
Welcome to UGC lecture series on computational mathematics, practical laboratory course for BSc electronics honors students. Today in the series we are going to see the fourth lecture. The topic of the fourth lecture is curve fitting. Basically we are going to discuss linear and quadratic fit from the data. These two fits are based on least square method. You will be given a set of data. From that you have to find a curve representing the data. The given input is a pair of values xi, yi for n pair of values you will be given. From that we wish to fit a curve which represents the given data. That could be a straight line or that could be a parabola, or depending upon the how the points are scattered, you have to choose the corresponding curve, either straight line or a parabola. So, this method describes techniques to fit the curve from the discrete data. The discrete data quite often occur in any practical computation. So, you will be getting a set of n pair of values, and for that you have to fit a representative curve. So, first we are going to see the representative curve as a straight line. Assume that these are the points x1, y1, x2, y2. Likewise, you have n pair of points scattered on the xy plane. Once again, this is the first point x1, y1, and this is x2, y2, and in general xi, yi, and xn minus 1, yn minus 1, xn, yn. You have n points on xy plane scattered like this. Our main aim is to find a curve. In this case, first case, we are going to see a straight line. We are going to construct a straight line based on the given data, which will represent the set of data. Okay. So, basically if you take a particular xi, the distance between that point and the line, so that we are going to calculate. If this is the scattered data and this could be the line. Suppose the scattered data are something like this, we can even fit any other curve. So, the idea is basically a minimum energy method, that is the residual error is minimized. Okay. Assume that we are going to fit a straight line. So, straight line is of the form ax plus b. So, this is our curve which we are going to capture. To capture this, we need to compute two values. What are the values? Values a and b. So, ax plus b is the data we are going to compute. To compute the straight line, it is enough if we compute a and b. So, these two values a and b are computed in the following manner. So, the distance between the given values xi, yi and corresponding point on the line. So, xi's are not varying, only the y value will be varying. So, if you calculate xi, yi, the distance between xi, yi and a point on the line xi, fi. So, we will be having this, and in fact, we are going to consider the square of the distances and sum of all the squares of the distances. That is why it is called the least square method. So, the sum of squares of such a distances will be For the first point it is y1 minus f of x1 whole squared. For the second point it is y2 minus f of x2 whole squared. Likewise for the last point y1 minus f of x1 whole squared. So, this is the distance between first point on the data and the corresponding point on the line, and this is the distance between x2 y2 and the corresponding point on the line, and this is the distance between the last point xn comma y1 and the corresponding point on the line. So, and you sum it, that error has to be minimized, that is the basis of the method. That is why it is the least, the error is minimized. So, it is the least error and you are calculating the squares distance, that is why it is called least squared techniques or least squared methods. Ultimately, I substitute the f value, it will be yi minus axi plus b whole squared. So, this summation 1 to n from the first point to last point, the distance between the point and the point on the line, that is in the squared distance, that has to be minimized. Okay. How to find a b so that the error is minimum? So, we will borrow some techniques from several variable calculus. Ultimately, the error function will be, the known values are xi, yi, unknown values are a and b. So, the error function is a two variable function a b. So, we have to identify a b in such a way that this error is minimum. So, the error function is minimum. So, you will be borrowing from the minimization of a two variable function techniques from calculus. So, this is once again I will repeat that, what is the main question, how to find a and b so that the error is minimum. So, the best line has a minimum error between the line and the given data, and this is called the least square approach. Since the squares of the error is minimized, it is called as least square, and this is the, once again I recall the error function that has to be minimized. So, it is basically a function of two variable, two parameter a and b. To minimize a two variable function, the necessary condition is the partial derivative with respect to a has to be 0 and partial derivative of this function with respect to b has to be 0, that is the necessary condition. Basically, the gradient of this function has to be 0. Take the derivative of the error with respect to a and b and set each to 0, that is the principle which we borrow from several variable calculus. A minimization of a two variable function, the necessary condition is the gradient has to be 0 of the two variable function. Basically, the partial derivative of the error function with respect to a and the partial derivative of error function with respect to b have to be 0. So, that is what we are writing, dou error by dou a has to be 0, and similarly for that. If you calculate based on that, the derivative will be incorporated within the summation, and here also the same technique will be incorporated. By that we have the following one. It is very easy computation, you can just refer back. If I calculate the derivative of this with respect to 2, you have outer function is square, inner function is yi minus ax plus b. So, you have to use the chain rule 2 times that function multiplied by the derivative of the inner function. So, which will give you this, and similarly for the other equation we will be having this. You can carefully observe that you had a square. So, based on the chain rule, minus comes because of this term. When I differentiate with respect to a, I will have minus xi. So, you have minus 2 times xi and the linear term. Similarly, when you differentiate with respect to b, there will be a minus 2 term only. So, this is the necessary condition for minimization of two variables of the error function with respect to a and b. And solve for these two equations for a and b, we will get a and b, and that will substitute in the linear equation, you get a linear fit. We will see how we solve these two equations for a and b. The first equation, once again I will recall the first equation. If I equate it to 0, number 2 it is not 0. So, if I expand this, summation I equal to 1 to n xi yi will be there, and a summation xi times axi. So, you will have a summation xi yi term, summation xi square term and summation xi term. So, similarly here you have summation yi term and the summation xi term and the summation constant term. So, if I simplify these two equation, I get the first equation, carefully listen to that, a xi squared and summation b xi, and the other thing you can take it to the right hand side, a times summation xi squared plus b times summation xi equal to the right hand side known values. Similarly, the other equation a times xi plus b times summation 1. So, you are counting 1 from for n data points. So, you will get n. So, these are the crucial equations called the regression. These are the main equation which will help us to compute a and b. Here it is a and b are the unknown. So, you have two equation and two unknown, a and b are the unknowns, other things are known because we are given xi and yi. So, you can calculate summation xi, this term can be calculated, and summation xi squared can also be calculated, summation yi can be calculated, summation xi times yi can be calculated, and n is known. So, the coefficients are a and b and the right hand sides are known. So, you can calculate, put it into a matrix form, we get this. You can see that a and b are unknown. I just I am writing b comma a. So, second equation is taken the first equation is taken to the second. So, I have b a I am writing. So, n times b and summation x times a equal to, so you get the second equation. Similarly, summation xi times b, so this term plus summation xi squared term, this term, that is equal to the right hand side, this term. So, you can conveniently put it in the matrix form and you can solve for a b, use any matrix solving technique to compute a and b, and I am getting the formula a can be calculated like this. So, basically you are computing the determinant of that, and you are multiplying the computing the inverse and multiplying. So, you have a is what, all known terms n times xi yi, you are getting xi yi for n pair of values. So, you can compute xi yi and you can add it, that will be this term, and summation xi you can calculate, summation yi you can calculate, that will be multiplied, and all are known terms. So, from that a can be calculated and again b can be calculated in the similar way, all are known terms, summation yi's, summation xi squared, summation xi, summation xi yi and summation xi squared, all are known terms. So, from these known terms you can calculate. So, what are the known terms you need? If you are supplied xi yi for I equal to 1 to n pair of points you have, you need to compute the sum of the xi terms, sum of the yi terms, sum of the cross product terms xi yi and sum of xi squared terms. So, then all are known, you can compute a b, and we will see one example that the given data points are 1 comma 0.5, 2 comma 2.5, 3 comma 2, 4 comma 4, 5 comma 3.5, 6 comma 6, 7 comma 5.5, these are the xi yi's, and you have to fit a straight line for these data points. So, summation xi I am adding. So, you can see easily verify that the summation 1 2 3 4 see it is n into n plus 1 by 4 2. So, you will get 28, and summation yi, the sum of all these values, that it has come to 24, and the summation xi will be 119.5, summation xi squared will be 140. So, you need summation xi, that is 28, summation yi, that is 24, summation the cross product term xi yi, that is 109.5, and summation xi squared, that is 140. So, you have all these things, summation xi yi, summation xi, summation yi, summation xi squared. We need the average mean of x bar and mean of y bar. So, now this will be the calculation for computing a, and this will be the calculation for computing b. So, I am getting a to be this number and b to be this number. So, the straight line fit is a x plus b, that is b plus a x 0.07142857 plus 0.8392857 x. Basically, this is the linear fit for the given data points. And now we will see the pseudocode of that. Basically, the pseudocode for linear fit we are discussing. This is the algorithm for linear fit. What are the inputs? We need n, the number of points, and xi, yi, the pair of n pair of values for I equal to 1 to n, and a and b are output. So, look at the input is the number of data points, and xi, yi the n pair of data points, and output a the coefficient of linear term, b the constant term. Okay. So, I have to compute how many values? 4 values I have to compute, that is summation x, summation y, summation xy, summation x squared. So, initially these are written in the sum variables, the variables are sum x stands for summation xi or 1 to n, sum y that stands for summation yi for I equal to 1 to n, sum xy stands for summation xi yi for I equal to 1 to n, and sum x2 that stands for sum x squared, summation I equal to 1 to n summation x squared. So, these variables are initialized here, they are initially 0, and for I equal to first point to the last point 1 to n, every time increment you update this variable, that is previous value plus the corresponding term. So, for sum x it is the whatever you have computed the previous value plus the current xi, and similarly sum y whatever the value sum y you have to add the corresponding yi, the present yi. Similarly, for xy you have to do that, update the variables xi with xi yi and sum x squared. Okay. Now, calculate the x mean, xm means for x mean, that is sum x by n, and ym is sum y by n. Now, a is calculated using the formula which is given just now we saw that the a calculation formula, and n times multiplication, n times sum xy minus sum x times sum y divided by n times sum x squared minus sum x whole squared. So, that will give you linear term, and b the constant term will be y mean minus a times x mean. So, you return the value a and b. So, this is the pseudocode for that algorithm. One more clear explanation of the algorithm is regression subroutine x y data n, and you have the a1 is the linear term, a naught the constant term. So, the variables are initialized, and for one to first point to last point you do this calculate and compute x mean y mean, and compute the first term n times sum x y minus sum x times sum y divided by n times sum x squared minus sum x whole squared, and similarly the constant is y m minus a 1 times x m, and you are computing the standard deviation in regression line which is not recorded here. Ultimately, you will compute a naught and b naught, you return it. Some situation we will be having the following scenario in practical, some practical application, that is the engineering data is poorly represented, because the data will be scattered in a particular different manner. If you fit by a straight line, that will have that may not be a right thing, you will have more error. Try to minimize the error, even that will not be a correct representation. So, in such a situation we have to go for beyond a straight line, could be a parabola. So, that we will discuss in the following slides. See, look at here, suppose if that scattered data points are like this, like a bend type one. So, here if you try to fit any straight line in any manner, that will not represent, rather a parabola could be a right representation for this. So, a parabola is preferable. In that situation, fitting curve in the following form, a constant term plus a linear term plus a quadratic term. Of course, the error which we are going to calculate, and that we are going to minimize as what we have seen in the previous case, linear case, just an additional term will be there. So, error is what? Distance between the data points xi yi and the point xi yi on the curve. So, that will be this, and square of the distance we will have this, and ultimately you want to minimize the error. So, if I minimize the square, the second degree term, and you will get these equations, standard equations, and these are the equations which will help to compute A naught, A 1, A 2. And look here, the same set of equation can be reformulated in the following way. So, what are the terms? The unknowns are A naught, A 1, A 2. The coefficient of unknown we will see, you have n, which is a known term, summation x I, again you have a x I y I data point, summation x I can be calculated, summation x I squared can be calculated, and summation x I y I can be calculated, summation x I cube also appearing, that you can be calculated, summation x I power 4 can be calculated, summation x I squared y I. So, you can calculate everything, and ultimately we will end up with a system of 3 equation in 3 unknown A naught, A 1, A 2, that we want to calculate, and solving these 3 the set of the matrix, you will get A naught. And now we will see an example for that. You have x I y I 0, 2.1, 1, 7.7, 2, 13.6, 3, 27.2, 4, 40.9, 5, 61. So, the summation x I is 15, summation y I is 152.6, and x squared we are calculating, summation x squared is 55, and x cube we are calculating, summation 225, and x power 4 we calculate, that will be 979, and x I y I we need that calculation, summation is 585.6, x I squared y I also we calculate, that will be 2489. These are the values which you need it, summation x I cube, summation x power 4, and all these things we calculated, and this is the system of 3 equation, 3 unknown, which for which we have to have we need to solve for A naught, A 1, A 2, and you can adopt any method for a 3 by 3 system. We obtained A naught, A 1, A 2, and this is the solution, the quadratic fit for the data, and we will see the pseudocode for the quadratic fit curve fitting. As usual, the inputs are the n number of points, x I y I equal to 1 to n points, a b c, a the quadratic term coefficient, b the linear term coefficient, c the constant term. Okay. So, you need to compute summation x squared, summation x cube, summation x power 4. The variables sum x stands for summation x, sum x 2 stands for summation x squared, sum x 3 stands for summation x cube, sum x 4 stands for summation x power 4, okay, and as usual sum y, summation x y. So, we compute at the end, ultimately we will be getting a 3 by 3 equation, and this is the 3 by 3 equation, and you solve, you get a b c, return that. So, the summary is that in many practical computation in science and engineering technology, quite often we will be obtaining a set of pair of data points x I y I for n set of that. So, we need to represent that data by a curve, a suitable curve, in what manner? With a minimum error, either it in the straight line form or in a parabolic curve form. Okay. So, the purpose of curve fitting is to represent the set of discrete data in the form of a curve in such a way that the minimum error should be a minimum. Okay. And of course, discrete data often occurs in practical applications. So, the numerical methods which enable the concept of simulation based engineering. So, we can use computers in modern era, we have sophisticated computing technology. So, you can go for you can use numerical technique, write a code based on the algorithm, that is pseudocode, you can convert into code and write that. So, in this lecture we discussed linear fit and quadratic fit so that the students can understand the meaning of linear fit and quadratic fit. The basically a given set of scattered data, we try to represent the data by a straight line or a parabola. So, here I would like to mention some questions. One, for the following data you can compute the linear fit as well as the quadratic fit. So, x, y. So, data are 0, 12, 5, 15, 10, 17, 15, 22, 20, 24, 25, 30, obtain a linear fit and quadratic fit for the above data using least square method. Second question, write programs based on the pseudocode and run for large data. So, we had seen as the fourth lecture curve fitting. Curve fitting is a technique based on least square method in which we try to represent scattered data in the form of straight line or quadratic. So, I thank the students for patiently listening to this lecture. We will see for the next lecture on different topics. Thank you very much.